Hi, are you interested in next generation AI chip? Do you know how to make it more efficient? I hope you will find this video helpful. My name is Huimin Zheng. I'm from Emerging Device and System Group at Hong Kong University of Science and Technology. Today, my topic is mixed precision in-memory computing SRAM macro based on child sharing. In this video, you will get an overview of in-memory computing and learn how circuit optimization techniques can be applied to improve the performance and efficiency. Before we dive in, let's talk about the memory. Memory usually refers to DRAM. In the left figure, the purple line is the size of AI model, and the blue line is the size of AI chip's memory. Note that the vertical axis is on a log scale. There is a significant gap between supply and demand at the current stage, which highlights the need for much larger memory size and bandwidth. In the right figure, it is the performance of the memory and the processor core during the past few decades. It's also on the log scale, and the huge performance gap is because they are based on different technology process and working principles. Therefore, memory has become the limiting factor of the system performance, and this is the memory wall. Then, how about just making the memory larger and faster? Well, it's not that simple. Let's look at the modern computer architecture, the von Neumann architecture. In the von Neumann architecture, the memory unit and the compute unit are separate. The on-chip ALU fetches data from off-chip DRAM to do the computing. It is clear that the speed of DRAM is roughly 2 orders of magnitude slower than the register within ALU, and the energy consumption of DRAM operation can even reach 3 orders of magnitude larger than the computer operation. So when it comes to computationally intensive tasks, there is substantial amount of data transfer between memory unit and compute unit, and most of the latency and the power consumption comes from the memory access rather than computation. Therefore, simply increasing the memory performance is far from enough. We need to address the data transfer bottleneck. Now, we are introducing in-memory computing architecture. In the in-memory computing architecture, there is on-chip memory that stores the data and performs major computing workload. The architecture is highly suitable for neural network applications, which involve lots of multiply and accumulate operation or MAC operations. The model weights are fixed after the model training, so they can be stored in on-chip memory. With minimum data transfer with off-chip memory, it can perform computationally intensive MAC operation, which substantially improve the energy efficiency and throughput. Now, let's look at conventional design for charge-based in-memory computing with 4-bit weight precision. Array performs MAC operation of X input and W weight. The partial product sampled on the unit capacitor C0 and accumulated on the MPhil line, which further sampled on the binary sized capacitor, and it performs 4-bit weighted summation when the sharing switch are turned on. In the middle are the balancing capacitors. In this circuit, there are several challenges. First, we need to improve the area and the energy efficiency of SRAM array and ADC. Second, the scalability is limited by the binary sized capacitor, since it's only 4-bit weight, but when it comes to 8-bit weight, it is very difficult to achieve it in the circuit. Third is the flexibility is limited by the fixed capacitor configuration. Say I want to implement 2-bit weight in this 4-bit circuit, then half of the circuit will be left unused. We can even go further to realize mixed precision in memory computing. Since each kernel has different sensitivity in the model, it is good practice to have finite quantization granularity, and this is mixed precision in a single layer. It has become increasingly important for quantization of the large language model, since there are so many parameters that we would like to make the model size as small as possible while still maintaining relatively high accuracy. Now, our goal is to design an in-memory computing circuit with precision scalability, flexibility, and support mixed precision applications, as well as maintaining relatively high area and energy efficiency. Now, introducing cascaded charge sharing array. We pick the 4-bit weight to demonstrate the principle. The weight is in 2's complement, where W3 is the sign bit and W2 to W0 is the magnitude bit. The Y is the result of the MAC operation of input X and the weight W, and it can be derived like this. For the circuit part, the voltage V are sampled on each column, and the sharing switch are turned on and off serially, performing cascaded charge sharing with each column. In this way, the voltage difference at the differential ADC is corresponding to the MAC operation result. Thus, the in-memory computing is achieved. Note that the rightmost column here is the dummy bit, which means the voltage is 0, and the leftmost column is the sign bit without involving any charge sharing. So this is the circuit diagram. The red part is for the sign, the blue part is for the magnitude, and the green part is the dummy. The weight precision can vary from 2-bit to 8-bit. However, two issues can be clearly observed. First, the overhead introduced by dummy bit degrades the area efficiency. Second, the multiple switching steps leads to reduced throughput or time efficiency. To improve the area efficiency, dummy bit removal technique is introduced, and to increase the throughput, pipeline architecture is adopted. After removing the actual dummy bit, we still need a virtual dummy. Then there are two strategies. Strategy A, the red one, is to let the next sign bit to serve as the virtual dummy, while strategy B, which is the blue one, is to let the former magnitude bit serve as the virtual dummy. And to achieve this, an additional switch are needed. Therefore, there are switch A and B. And the switching timing diagram for these two strategies are similar. It seems that strategy A is superior because the sharing signals arrives earlier than strategy B. But the situation becomes complicated when it comes to the pipeline. Before introducing the pipeline, let's look at the timing diagram of the conventional in-memory computing circuit. The first input is sent for MAC, followed by the ADC. The second input can only be processed after the first is finished. For MAC, it usually takes 3 clock periods. First, reset. Second, multiply. Third, accumulate. So usually 3 clock period. And for ADC, it depends on its bit precision. it usually for 8-bit ADC, it usually takes about 10 clock period. Therefore, the throughput is actually limited by the ADC because ADC takes a longer time. So when it change to the pipeline structure, there is a time margin for the MAC operation, which is exactly what we require. After calculation, the 8-bit MAC operation in our design requires similar amount of time as the 8-bit ADC. So the pipeline is fully utilized and throughput is nearly unchanged. Here it shows the pipeline diagram on 5-bit wait as an example. At the beginning, send the first input. The yellow part is the MAC operation involving dummy bit sharing and cascade sharing. Then the ADC starts working and turns red. At the same time, sending the second input, and at this stage, ADC and the MAC work simultaneously. After ADC finishes and output the final result of the first input, then the intermediate result of the second input is ready. So it only takes 3 clock period for reset and sharing, and then the ADC starts working again. So this is for 5-bit wait. For 8-bit wait, the gap here is exactly filled, so it can fully utilize the benefit of pipeline. And this diagram is for strategy B as the magnitude bit as the virtual dummy. Because the sign bit is not available during ADC running, therefore, strategy A cannot benefit from the pipeline. Here is the pipeline performance. On the left is the performance comparison between strategy A and strategy B. The x-axis is the wait bit width, is the precision, and the y-axis is the latency. The lower the latency, the better the throughput. For the strategy A is the red line, and the strategy B is the blue line. You can see at stage 1, which is the solid line, the strategy A is better. But for stage 2 or stage 3 or more, the strategy B is better, and because it converts to 13 clock period. So the takeaway is that for frequent wait updates, we should choose strategy A because we always stay at stage 1. But for frequent wait reuse, we should strategy B because it can benefit from the pipeline. You may ask why the wait will update. Actually, in the cluster-based SRAM circuit, the wait can be updated without writing new values, and I will show it later. And here are 2 points that for precision of 2-bit and 3-bit, because there is no other sharing bit, so the latency stays at the same high. And for strategy A, the wait precision lower than 5-bit, the latency is limited by the circuit setup. On the right side is the performance comparison between the conventional ones and the pipeline ones, and the green is the pipeline ones. The x-axis is the wait reuse times, and the y-axis is the average latency. We can see that the pipeline ones finally converge to 13 clock period, which leads to the throughput increased by 15% for 4-bit weight and 46% for 8-bit weight, which is quite a lot. This is a circuit implementation based on TSMC 65 nanometer node. The weight values are stored in the array. First, the digital input data converted into the analog voltage by this RDAC. Then the array performs MAC operation with the input and weight. And the output is sent to the ADC here for conversion into a digital result. The SRAM adopts a cluster-based structure, which with each cluster consists of 8 SRAM cells. During computation, one of 8 word lines is activated to update the weight. The product of the input and the weight is sampled and accumulated, depending on the SW switch A and switch B. Since the design requires a large number of switches, a non-cluster-based approach would lead to large peripheral circuitry, which significantly reduces memory density. Therefore, the cluster design represents a trade-off between memory density and compute density. The layout of the cluster is on the left, with a MOM capacitor of 4 femtofarad. Each row consists of 64 clusters, and each row shares a switch with its neighbors. There are 64 rows in the array. Each row has an ADC, but since not all ADC is active, power gating is applied to turn off the unused ones and save energy. The timing diagram is on the right. Here, on the left is simulated MAC values for different 8-bit weights. The intermediate result corresponding to different charge sharing steps, which demonstrated the flexibility in precision. On the right is the transfer curve. The x-axis is the MAC input is ideal MAC values, while the y-axis is the output analog voltage. The R square equals 5/9 after decimal point, so the linearity is excellent for in-memory computing. Here, the right curve is the power consumption versus bit precision. Higher bit precision resulting in lower power consumption due to the reduced number of ADC in use. The blue curve is the energy efficiency. At 4-bit, the energy efficiency reaches 281 tops per watt, and when normalized to 4-bit weight is 70.3 tops per watt, which is on par with the recent published result after scaling to the same process node. Okay, so far, we've finished the array part by adopting cascaded charge sharing, which enhanced both flexibility and efficiency. Now, let's move on to the ADC and see how the similar idea can be applied. Here, let me introduce our customized charge sharing ADC. Before that, I need to explain the conventional ADC and the challenges in the in-memory computing applications. Here is the diagram of ADC and its peripheral circuits. The conventional SAR ADC consists of binary-sized capacitors. Since there are numerous ADC functioning in parallel in in-memory computing application, this will result in substantial area and power consumption, particularly for high-precision ADCs. Therefore, we have to find a way to improve the efficiency. Second, the common mode voltage regulation. For different input values, the array output signal has large variations. The common mode voltage of the signals sampled by ADC spans nearly the entire swing, which can introduce errors in data conversion. So, we need to regulate or align the common mode voltage to a fixed value first, and then start conversion. But it usually requires a fully differential amplifier with common mode feedback, which incurs static power consumption. And third, the dynamic range variation. The output signal range varies significantly due to weight sparsity and kernel size. Take example, if there are lots of zeros in the weights, even the inputs are all ones, the output signals will still be very low. So to maintain a relatively high SNR, the reference voltage should be adjustable, but it requires a power-hungry reference buffer. Since the buffer is required to operate at a high speed, its substantial static power consumption can even far exceed the ADC itself. The operating principle of a charge-sharing SRAM is shown in the figure. First, the binary-sized capacitors are precharged, and the input signal is sampled onto the holding capacitors. Then, depending on the comparator's output, each binary-sized capacitor sequentially transfers its positive or negative charge to the corresponding nodes to compensate the differential voltage. This procedure is repeated for all bits, after which the input signal is fully digitized. So we can apply the same ideas here. Using the unit-sized capacitors combined with cascaded charge sharing, we can replace the binary-sized capacitors to achieve similar results, while substantially improving area and power efficiency. So this is the proposed 8-bit charge sharing SRAM. On the left is the common mode regulation circuit, which consumes no static power. On the top is the pre-charge sharing circuit for achieving binary weighted charge distribution with cascaded charge sharing. And the basic timing diagram is shown on the right. The principle of common mode voltage regulation works as follows. First, the sampling switch are turned on to sample the input signals. Due to the circuit symmetry, the voltage at the middle point corresponds to the input common mode voltage. Next, the common mode enable switch are turned on to force this middle point voltage to the fixed level. This voltage introduces no static power consumption. However, there is a trade-off. Because of the capacitive load, the differential voltage is attenuated by about 20%, given that the holding capacitor is 64 femtofarad in the design. In the right figure, the top lines represent the voltage of the input signals, while the bottom lines shows the voltage at comparison nodes. We vary the common mode voltage of the input signals, and it turns out that the common mode voltage at the comparison nodes varies by only 15% due to the parasitic capacitance at the shared node, like here. But this variation is acceptable because the differential comparator can tolerate a certain amount of common mode noise. In the pre-charge sharing circuit, the binary weighted charge distribution is achieved by cascaded charge sharing, as the bottom plate always connected to the ground. However, when the capacitors are connected during data conversion, a deviation in the common mode voltage can occur, and this may introduce error. This deviation is due to the parasitic effect. So ideally, when the top plate holds a certain amount of positive charge, the bottom plate should hold an equal amount of negative charge, ensuring symmetry. But in practice, parasitic capacitance disturbs the balance. The parasitic capacitance at the bottom plate does not accumulate charge, whereas the parasitic capacitance at the top plate does. As a result, the charge distribution is no longer perfectly symmetrical, leading to a deviation in the common mode voltage. And this common mode effect can be compensated by introducing an additional capacitor. For this capacitor, the top plate is always connected to reference voltage, while the bottom plate participates in the pre-charge sharing process. And in this way, the parasitic charge becomes perfectly matched, ensuring the common mode voltage remains fixed. Now let's talk about the adjustable resolution. According to the previous equation, the input dynamic range of ADC is determined by the total charge in the pre-charge sharing circuit. The range can be adjusted by varying the number of pre-charged capacitors. Since the charge distribution must remain binary weighted, the timing of the charge sharing switches should also be adapted. As the input range decreases, the resolution becomes finer accordingly. The figure on the right shows the ADC transfer curve for different input ranges. In the full range mode, both the DNL and NNL remain within 0.5 ASB, demonstrating excellent linearity. So this is the ADC performance. First, an effective common mode voltage regulation scheme was developed without static power consumption. Second, the pre-charge sharing scheme replaces binary-sized capacitors with unit-sized ones. The overall DAC and area and power consumption are reduced by more than 80%. Finally, the average power consumption of 8-bit ADC is about 17 microwatt at a sampling rate of 10.4 macro samples per second, and the power breakdown is shown below. So here is the conclusion. First, cascaded charge sharing is an effective technique that not only enhances the circuit flexibility, but also improves the area and power efficiency. And it can be applied to both the SRAM array and ADC. And because of multiple charge sharing steps, the pipeline architecture becomes essential to alleviate the throughput loss. It can achieve up to 46.2% improvement in throughput. And final takeaway, if scaling up seems challenging, consider scaling down instead. Thank you for watching.